sklearn, neighbors, neighborhood components analysis. Description: a dimensionality reduction method that learns a projection to a lower dimensional space that preserves the neighborhood structure of the data. It uses a nearest neighbors search to find the neighborhood of each data point and projects the data to a lower dimensional space that minimizes the distortion of these neighborhoods. Inputs: X the training input samples, where n samples is the number of samples and n features is the number of features. N components the number of components or dimensions to project onto. This parameter controls the dimensionality of the output space. Outputs: components the projection matrix learned by the algorithm. It has shape n features, n components and represents the transformation that maps the original data to the lower dimensional space. N features in number of features seen during fit. Feature names and names of features seen during fit. Defined only when X has feature names that are all strings. Steps: the algorithm first constructs a neighborhood graph where each data point is connected to its k nearest neighbors. It then learns a projection matrix that minimizes the distortion of this neighborhood structure. This is achieved by finding a projection that minimizes the difference between the distances in the original high dimensional space and the distances in the projected lower dimensional space. Metrics: reconstruction error. This metric measures the difference between the original data and the reconstructed data after projection and back projection. It can be used to assess the quality of the dimensionality reduction. Visualization plots: scatter plot. This can be used to visualize the data in the original and projected spaces. This helps to understand how the neighborhood structure is preserved in the lower dimensional space. Fine-tune parameters: n components. This parameter controls the dimensionality of the output space and needs to be carefully chosen based on the desired level of dimensionality reduction and the trade-off between accuracy and complexity. N neighbors. This parameter determines the size of the neighborhood used for constructing the neighborhood graph. A higher value for n neighbors leads to larger neighborhoods and potentially smoother projections. Uncertainty methods: confidence intervals. Confidence intervals can be estimated for the projected data points to quantify the uncertainty in the projection. Challenges and fixes: Challenge 1: high dimensionality of the input data can lead to computational challenges in constructing the neighborhood graph. Sample use case that resulted in challenge 1 when dealing with very high dimensional datasets, such as image data. Calculating the distances between all data points to find the nearest neighbors can be computationally expensive and time-consuming. Fixes to challenge 1: approximate nearest neighbor search. Algorithms use techniques like KD trees, ball trees, or locality-sensitive hashing to approximate the nearest neighbors and reduce the computational burden. Random projection: apply random projection methods to reduce the dimensionality of the input data before constructing the neighborhood graph, making the nearest neighbor search faster. Challenge 2: choosing the optimal number of components. N components is crucial for balancing dimensionality reduction and accuracy. Sample use case that resulted in challenge 2: a very low value of n components might lead to excessive data loss, while a very high value might not achieve significant dimensionality reduction. Fixes to challenge 2: reconstruction error. Monitor the reconstruction error as a function of n components and choose the value that gives a good trade-off between dimensionality reduction and error. Visualization: use scatter plots or other visualizations to inspect the data in the projected space and identify an appropriate value for n components that preserves the essential structure of the data. Challenge 3. The choice of the metric used to measure distances between data points can significantly impact the results. Sample use case that resulted in Challenge 3. Choosing an inappropriate metric might lead to poor neighborhood preservation in the projected space. Fixes to Challenge 3. Domain knowledge. Leverage domain knowledge to choose an appropriate distance metric that reflects the underlying relationships in the data. Experimentation. Experiment with different metrics and evaluate their performance based on pay, reconstruction error, or other relevant metrics. Visualization. Visualize the data in the projected space for different metrics to assess pay, quality of neighborhood preservation, and choose the metric that leads to the most desirable results. Challenge 4. The algorithm might be sensitive to the presence of outliers in the data. Sample use case that resulted in Challenge 2. Outliers might distort the neighborhood structure and lead to poor projections. Fixes to Challenge 2. Outlier detection. Use outlier detection techniques to identify and remove or adjust outliers before applying the algorithm. Robustness. Explore robust versions of the algorithm that are less susceptible to the influence of outliers.